Welcome to my presentation. My presentation topic is Design of BCD Adder using 3-input XOR and majority gates based on quantum dot cellular automata nanotechnology. And the contents of my topic are objectives, existing technology, proposed methodology, simulated results, and the references. Objectives: to design a BCD adder using 3-input XOR and majority gates based on QCA technology and to simulate proposed BCD adder on a QCA designer tool to compare the proposed technology with existing technology in terms of performance deciding parameters, area, delay, power dissipation for the simulated design, where the QCA technology consists the new nanotechnology. Lot of emerging techniques can natively realize majority gates, although enhanced gates such as exclusive OR are implemented by several match gates. The existing technology is the CMOS technology. CMOS stands for complementary metal oxide semiconductor. CMOS technology is the predominant technology for manufacturing integrated circuits. CMOS VLSI design is like a modular approach to the creating ICs. The working principle in CMOS technology, both N-type and P-type transistors are used to design logic function. The same signal which turns on a transistor of one type is used to turn off a transistor of other type. The limitations of CMOS are slow operating speed, requires large area and delay, relatively large power dissipation, difficult to implement. As CMOS technology reaches its physical limitation, new computing paradigms are exploited to push forward computational efficiency. New techniques that are implemented is the QCA technology. The proposed technology is quantum dot cellular automata technology. It is a new nanotechnology that may be used to overcome the limitations of CMOS technology in terms of power consumption and energy efficiency. The development of customizable digital systems is among the most appealing areas in QCA in terms of energy efficiency, integration density, as well as switching frequency. QCA technology is seen as a viable option for circuit implementation. QCA circuits are made up of the identical components known as QCA cells. QCA cell is similar to the shape of square containing of four dots at each corner and two charged electrons. Quantum dots, these are the nanostructures created from standard semiconductor materials. With QCA, these four dots are used for the representation of binary 0 and binary 1. It can be indicated by using polarization. If the polarization is +1, then the binary value will be 1. If the polarization is -1, then the binary value will be 0. QCA circuit or the majority gate. In QCA circuit, let's see the majority gate. Majority gate is the universal gate of the QCA logic. The majority gate function of three inputs A, B, C, denoted as M of A, B, C, acts as vector and evaluates to true if and only if at least two of the three inputs are true. It can be expressed in both disjunctive and conjunctive normal, where M of A, B, C equals to AB plus BC plus AC. And here the majority gets the three inputs A, B, C, and the output is M of A, B, C. Here performs the majority function. If the majority of two inputs will be true, then the output will be true. Here, if the output will be ones, where the majority of ones will be present at the input. And this is the QCA cell of the majority gates consisting of the 5 cells, where the 5 cells indicates 3 inputs, a middle cell and 1 output. The middle cell of 3 input majority gate switches major polarization and maintains a consistent output. If the polarization of one of the 3 input cells is constant to P, that is polarization -1 or +1, then this gate can be programmed to the function. The proposed digital circuit is BCD Adder, binary coded decimal is a class of binary encoders of decimal numbers where each digit is represented by a fixed number of bits, usually 4 or 8. BCD adder is a digital circuit that adds the two 4-bit BCD numbers. If the addition result is equal or less than 9, then the value of BCD sum and binary sum will be same. Otherwise, they will be differ by 6. As discussed in the before slide, let's see the operation of BCD adder. Here it consists of add and addition where the 4 bits will be added and the output will be generated. For this OR gate, if any of the inputs will be 1, then the output will be 1 and this 1 will be given as here. Here where we see the 0 is given to both LCB and MSB and the LSB and MSB at 0 sums if the output of this OR gate 1 is given as input, 0110 will be indicated. That is binary 6 will be found. That is when if the output of the BCD is less than or equals to 9, then no need of the 6. If it is greater than, then the 6 will be used. If the output is 1, then the 6 will be used. If the output is 0, the LSB and MSB are 0 and the both zeros will be represented. Thus, this can be treated as binary 0. And this 0 on the normal output, it can provide the BCD, binary coded decimal output. This is the operation of the BCD adder. When going to the basic circuits of BCD adder, to design BCD adder, we require AND and OR logic gates. In QCA, the majority gate can be used to implement the basic gates. The majority gate, it is the first figure as shown, and this is the majority gate when it is used as AND gate, and this is the majority gate when it is used as OR gate. And this majority gate, as we seen, it consists of 5 cells where there are 3 inputs, 1 middle cell and 1 output cell. In these 3 cells, 1 cell should be keep constant. As we keep constant here as this input cell as 0, it can be worked as AND gate. And if we keep the constant of C equals to 1 at here, then it can be used as OR gate. And we can realize many gates by using the majority gates in the implementation of their logics. The implementation of tool of quantum dot cellular automata is QCA designer tool, that is quantum dot cellular automata designer tool installed in a PC for designing circuits, where QCA designer can report the cell count and area. In terms of area, it is implemented by measuring the outline of QCA layout. The calculation is feasible for single layer designs. And the advantage of QCA are less area, low cost and low power consumption, where it overcomes the limitations of CMOS. The power can be reduced and efficiency can be implemented. Where comparison of different simulation engines, and it is the proposed design of BCD adder with QCA layout. It is simulated in the QCA designer tool, and these are the simulated results that are output for the proposed design BCD adder. At last, I conclude that majority logic has been widely used in emerging computing nanotechnologies. By realizing the layouts of the proposed designs using QCA technology in QCA Designer, we have obtained promising results in both area and delay. The BCD adder is a financial, commercial, and industrial computing technique. We implemented the design to logic representations are validated using different types of binary adders as well as QCA design strategies. Thus, the BC adder is widely used in the commercial and computing techniques. We choose the BC as the best option to be designed in QCA technology. These are the references we use it for the proposed technology of BCD adder using QCA technology. Thank you. 9 weeks.